Hello? Sounds better. Yeah. Yeah. It should work, right? All right. That's the so let's start with the motivations. So the idea idea or proposal of the topological symmetry or SymTFT have been discovered but in high energy communities. Okay. The basic idea is the following. It says that a gapless quantum field theory, essentially a gapless quantum field theory, okay, can be split into a sandwich such that the bulk is topological. It's called SymTFT. On the one side of the boundary is gapped. The other side of the boundary is gapless. Could also be gapped if you study gapped phase. Okay. The gapless part only contain what the people call containing only dynamical part, the dynamic information, and the gapped boundary contain the symmetry information. Okay. So the gap boundary encode information of non-invertible symmetries. Uh, I don't have pointer, right? So I have to use my hand. It's okay. It's okay. I can use the mouse. Oh, this one. Oh, ah, wow. Let me use my hand. Okay. So the gapless boundary containing information on dynamic data. Okay. Although this idea was shown to be very powerful in the study of gapless phases through various examples, it was not shown why it works in the following sense. There is no proof that why why this splitting is always possible. And also a related question is how many splitting do you have? Okay. If it is not unique, how many do you have? Among all of them, do you have a canonical one, or what do you mean? What do you mean by splitting this in this way? Okay. However, this type of answer have been answered already in some early work of by myself and Zheng Hao. Uh, our theory will tell you that okay, this splitting in general, you can have an infinite number of splitting, and but there is a canonical one. So we believe, according to our more complete theory, what physicists have referring to is that canonical one. I'm going to show you what that canonical one really means. Okay, so uh, so let me start from the story by recalling to how we get there. How we get there. Of course, it's quite different philosophy underlying the the logic. Okay, so what we did is that we first start with the notion of morphism. Let me first recall the notion of morphism in mathematics. A morphism between the two mathematical objects of the same type, for example, group, algebra, representations, categories. Um, we require the morphism to preserving the defining structure of the mathematical object is arguably the most important notion in mathematics. So in mathematics, if you introduce a mathematical object, you have to tell me how to define morphism. Otherwise, the definition is incomplete in some sense. Okay. Okay. And you can arguably is the most important. What do I mean by arguably the most important notion in mathematics? Because every other notion in mathematics can be defined using the notion of morphism. So morphism is the most fundamental one. You can use it, you can use it to define everything else. Okay. Even if you like, you can define the notion one using it if you like, if you're familiar with category theory. Okay. And for example, the notion one can be treated as the terminal object in a category set. Okay. Ironically, such a notion for physical systems such as quantum field theory have never been introduced in physics until 2015. So in 2015, we introduced a notion of morphism. Well, this morphism is not just ordinary morphism. It have to preserve the structure between two topological orders. Well, we use the topological order for convenience. Of course, this can be generalized to other quantum physics or quantum field series. Okay. In this talk, I will review this notion and its application in the study of topological order or quantum liquid. In particular, we will show that it naturally leads to some consequence. One of them is a boundary bulk relation, and the other is a topological weak rotation. And the later one, which include the category symmetry and the symmetry TO correspondence as a special case. We will show that a morphism between two QFT is more precise and fundamental structure underlying the idea of topological symmetry and the SymTFT. Why is that? So how to define the morphism between two quantum field theory? So a well-known answer. A Euro definition of morphism between two quantum field theory is a domain wall between two quantum field theory. Okay, so I draw the domain wall here. QFT1, QFT2, there is a domain wall. And the domain wall provide a physical realization of a mathematical notion of a bimodule because the observable or operators, non-trivial operators living in the quantum field theory one can clearly fuse into the domain wall. So provide a left action, okay, on the domain wall. Similarly, the fields or observable in the quantum field theory two can fuse from right. So domain wall simply provide a physical realization of the mathematical concept of bimodule. Okay, so the two-side action. All right. However, such a definition of morphism, a bimodule, is less fundamental because it does not preserve the algebra structure of quantum field theory. As a consequence, such a definition of morphism as a bimodule only distinguish quantum field theory up to Morita equivalence. Okay, so that means this definition, although it's natural, is well known, but it's not good enough. Okay. So in mathematics, there is a more fundamental natural notion of a homomorphism between two algebra objects. So let's record them. Group homomorphism. What is group homomorphism? Consider two groups. F is a group homomorphism. That means it have to preserve structure. That means the FG1, G2 will split as a FG1 times FG2. Okay. Similarly, you have algebra homomorphism also needs to satisfy this condition. Okay. The question is, what is the physical realization of a notion of algebra homomorphism or equivalently? Equivalently, how to map a quantum many-body system or quantum field theory to another such that algebra structure or operators or observable are preserved? I think this is a very natural question. Okay. Um, a side remark. Before before we did this, we were kind of surprised that no physicists have been trying this. We searched a little bit, we didn't find it. But I feel like in physics, the repetition theory is well known. So people know the action very well. Operator acts on something on a hyperspace. So the repetition theory is very well known. But to consider algebra homomorphism between two algebra um, seems quite strange. Okay. At that point, I don't know anyone have thought about this or not. Okay. So we have been puzzled on this for a while ourselves. Okay. So yes. Yeah. Yes. Right, right, right. But there is no morphism. What is the morphism between two CFT? I know. Yeah, yeah, yeah. Right, right, right. Right, right, right. I agree with you. That means when the CFT have an algebra, a precise algebra description, then you can consider just ordinary algebra homomorphisms. Yeah. But here I'm considering very general. Yeah. Yeah. Oh, sorry, I forgot. Can I make a comment? So no matter how we're gonna do in our setting, we should recover the case you mentioned. Yeah. Sorry. Yeah. 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 What do you mean? The domain wall is well defined. Is that what you mean? Morphism between TQFT, I haven't introduced yet. replace QFT by TQF. So TQFT have some other definition. So mathematically, there is some other obvious way to define it. For example, Wang Yinan asks for CFT. You can consider CFT in a different way, even as a monoidal functor between the cobordism category to the category vector space. From that context, you can also define algebra homomorphism as a natural transformation between monoidal natural transformation between two monoidal functors. That you can also do that. For topological field theory, there is also a definition in that way. Yeah, yeah, yeah. But here is slightly different. Yeah. So maybe I shouldn't claim that. So I should take it back. That I shouldn't say that the QFT nobody have thought about this because it depends on the context of how you formulate it. Yes. Yeah, in that would be more precise. If you use the cobordism and functor from cobordism category to a linear category, then there is a natural definition there. Okay, more mathematical definition. Okay. Uh, but this one is quite oh, okay. Before we introduce the notion, we need some preparation. Okay, the term topological order in the following few slides will be replaced eventually by much more general concept like quantum liquid. However, the notion is that it's harder, much harder to define. Okay, so I'm not going to use it. I'm just using topological order for now. Okay. Therefore, for convenience, we restrict our discussion to a familiar notion of topological order at first. Okay, we will come back to the. Okay, so a topological order is called anomaly free if it can be realized by a lattice model in the same dimension, and it is called anomalous otherwise. Okay, that's the one notion we need. For example, the gapped boundary of a non-trivial topological order are example of anomalous topological order. Okay, a gapped boundary of a trivial topological order is an anomaly free ND topological order. Okay, if the bulk is trivial, then itself is anomaly free. Just terminologies. Why I need that? Because I gotta do something. Okay, so if a potentially anomalous ND topological order has a unique n plus 1D anomaly free topological order as its bulk, denoted by this. This is you can call a hypothesis. Actually, in the 2014 paper, we provide a physical proof of this. Okay, why I need that? Because I just Okay, so anomalous topological order, because it cannot be realized by a lattice model of the same dimension, but it must be realizable as a defect in a higher dimensional lattice model, right? It's still finite dimensional, still finite. If it is infinite, if suppose a topological order can only be realized in a lattice model of infinite dimensional lattice model, then we can safely say such anomalous topology doesn't exist. Okay. So we still assume to be finite. So this is a picture to illustrate how the realization of that. So this topological order is realized the higher codimensional defect in a lattice model of higher dimension. Okay. If this is realized, what you can do is that you drag this point. Okay, you drag this point to make it looks like a cigar. Okay, and you push the cigar to this in this way, and this A become a boundary of a one-dimensional higher bulk. Okay. This argument seems to show that, okay, in general, this realization is not unique. You can always find a lot of different realization of this situation. Okay, lattice model is not unique. However, if you do this dimension reduction, the proposal we give here is that after dimension reduction, we obtain a unique bulk of AN. That's our, you can call it hypothesis if you, because I didn't show you proof anyway. So importantly, AN should be understood as a boundary phase, which include the neighborhood of the boundary by definition. This remark actually also tell you how to prove it in some sense. Okay, because the bound the boundary phase by definition include a neighborhood of the boundary. I'm sorry. Okay. Why is allowed to? Well, this is just a lattice model realization. In general, you have a non-unique. Why allowed? You can always do that. Yeah. But you gotta have you will end up with the same phase. That's the argument. Well, I didn't show the argument, but the statement is clear, right? I didn't want to go to the detail of the proof. This realization in general never unique. We only talk about the existence of such thing. Okay. But after you do this, after you do the dimension reduction, we claim this have to be unique. Uh, let's just accept this for now. Okay. I don't want to go to the details. Okay. All right. So now we can give you some example. Um, so for example, if you have a situation like this, the D is a domain wall, right? Then A is not a bulk of D. Okay. If you talk about the bulk of D, you have to do a double folding. Okay. Then this double layer system become the bulk of D. Okay, that's one example. Okay. So similarly, if you have a anomaly-free topological order A of the dimension n, okay, you can simply label a trivial domain wall. Trivial domain wall is A. You can label the trivial domain. You can view it as a one-dimensional lower topological order. Okay, trivial domain is viewed as a one-dimensional lower domain wall. Then you do double folding. Then you got this result. So the bulk of this one is a double layer. Okay, that's a typical example you need to keep in mind. Oh, this is just some kind of a because some kind of orientation was changed because you move this way, the normal direction have been changed. So you need to do some slight modification of this. It's just a way to recording the orientation. That's all. On the categorical setting, if you study observables, there is slightly change. For example, in the 2+1D topological order, if you do that, um, the uh, uh, the braiding become anti-braiding, that kind of thing. Yeah. Yeah. It's just like this. So the special case of that we would denote as the bulk of D equals to that. Yeah, bulk of D will be double layer, and this is just a notation for stacking of two topological order over the empty space. That means there is no coupling between these two layers. Okay. Yeah, we could go slowly. Oh, then we give a notation for trivial topological order. We just denote as one. Okay. And the bulk of trivial phase have to be the trivial. So bulk of the trivial topological order is trivial one. Okay. And AN is anomaly free if and only if its bulk is trivial. A bulk is trivial. That means that you can realize that as a lattice model of a one-dimensional lower, right? In some sense, this is trivial. Bulk is trivial. Well, if you talk about topological field theory, you got to be careful. Sometimes there is also issue about the bulk is invertible. That's a different matter. But here, I mean trivial. But then, if you agree on this, you will see an immediate consequence. If you have a topological order, you consider its bulk. Remember, the bulk is already the one you got from dimensional reduction. It's already saturated, okay? And itself is normally free. If you consider bulk of a bulk, so the bulk of this one is empty, okay? So the bulk of bulk is trivial. This statement perhaps is not trivial because we know in algebraic topology, there's a well-known statement that it's called the boundary of boundary is empty, and this is the starting point of homology theory. So we believe that this will lead to a cohomology theory eventually, but we don't know what it is. Okay. DA, it's also called the gravitational anomaly of A. Yeah, it's just anomaly. Yeah, exactly. No, there are no invertible phase there. This is trivial. Oh, in that case, In that case, I don't know what kind of the statement I should make. I need to be careful because what I'm saying is that in that case, perhaps it's still okay, but it depends on how you formulate the cavity. Because you see, the way we formulate this, already using the condensed matter picture, topological order can be defined on the open disk. Yeah. So you should view them as a TQFT defined on the open disk. But TQFT defined on the open disk is slightly different from TQFT because you only consider a space-time of a certain type, a space-time manifold of certain type. Very often, if you consider a non-trivial space-time, you might have a framing anomaly. But in this case, you don't have that issue. Wow. This is condenser. So that means that for quantum Hall system, for condensed matter physicists, it is anomaly free. But for rest-seeking TQFT people, that's anomalous because there's a framing anomaly, and that's according to that's amounts to the same statement, equivalent statement that the associated the 3+1D bulk is invertible, right? It is a subtle difference. Yeah.
Can
Okay.
I ask a
Now,
question?
yeah. Okay.
So for perturbative anomaly, I think the bulk of the bulk is where the anomaly polynomial is defined, right? So is that different from the bulk of the bulk that you were talking about?
I'm sorry, can you ask it again? I didn't catch the question.
So for perturbative anomaly, I would expect the bulk of the bulk is where the anomaly polynomial defined. Is that different from the your statement where the bulk of the bulk is trivial?
I don't know. What's the anomaly polynomial? Is that what you mentioned? I
That's so usually you have a characteristic class in D plus two dimension, which reduce to the Chern-Simons action in the bulk in the standard bulk.
I don't know. I don't know how to answer the question.
Or maybe did by anomaly you're referring to the
I'm referring
non-perturbative
to
anomaly.
yeah, I'm referring to the bulk as the gravitational anomaly.
Okay.
Yeah, well, the anomaly you're referring to, you have a geometric way to catch the anomaly. Whether it can be put in this setup, I have no idea. I don't know.
Sorry, but for gravitation anomaly, the roof genus is also defined in the D plus two dimension, right?
I don't know.
So that's
Sorry.
so
Yeah.
yeah, maybe the language is a little different.
Yeah, maybe the language I'm not so quite understand the question, or maybe someone in the audience can explain that to me. Or
Or maybe we can
ah
ask later. Yeah.
yeah, yeah. So perhaps that's relate to the question that we were talking about TQFT. For condensed matter, that this is okay. Yeah. But if you consider more complicated, if you allow TQFT, allow more complicated space times manifold, then it becomes subtle. So, so maybe, yeah, I remember when I gave this talk, I have um, many years ago in Harvard, the first time I gave this talk, Dan Fried was really upset about this. Well, it's about the issue about the meaning, whether you have anomaly or not. I think there is a difference. So in the end, we persuade him after a lot of argument that you have to consider different type of QFT. So we call it the H type and L type. So he also in the so maybe 2 years later, he wrote a paper with Michael Hopkins to have a section to discuss the H type and the L type of QFT um, separately. Yeah, they have a different meaning. Yeah. So this condensed matter people, for condensed matter people, they will think about this so-called H type. Well, H refer to Hamiltonian, on the lattice model on the open set, but Lagrangian is different matter. Yeah. Yeah, but this is a yeah, it's good discussion, But if the two community using different language, the bulk of the bulk is trivial for generic quantum field theory. If you're using L type of quantum field theory, that will be a issue. Yeah, it's not. I don't
Is there
know how to make sense of that. myself.
Sorry, I couldn't hear the comments from the audience. Um, but
Oh, some okay, maybe the one of the audience give the remark saying that he had a similar question as yours. Okay, so I just
I see.
just made it. So this issue of bulk and the bulk is trivial might not shouldn't hold for generic TQFT in this defined by corporatism. If
I see.
you define TQFT in that setting, or if you use the consignment action, that also have problems. Yeah. So
I see.
this you can view this
Thank you.
as a condensed matter people's so topological order should be viewed as quantum topological field theory defined on an open disk. Yeah. Then you don't have the framing issue. Okay. All right. Let's continue. So now we introduce a central concept called the morphism between two topological order. They both um, they both having a gap bulk. Okay, so that means they're potentially anomalous. Well, if the bulk is trivial, then it's anomaly free. So this including anomaly free case, but also including anomalous case. Okay, it's just a domain wall between the bulk of A and the bulk of B. So this is the bulk of B. This is the bulk of A. Between these two, you can introduce a domain wall. Now the requirement is that this domain wall fuse with A, give you exactly B. That's the definition of morphism. I want to give a intuition why we want to define the morphism in this way. Oh, maybe in the next slides. Okay, so if we define morphism in this way, the composition of two morphism can be easily introduced. Okay, so a morphism from A to B is a domain wall between bulk of A and the bulk of B. A morphism from B to C is a domain wall between bulk of B and the bulk of C. Okay, so then you can simply fuse these two. You got the compositional morphism fusing two domain walls. So this uh uh yeah, this concept automatically give you a notion of how to compose two morphisms. Okay, why we introduce a morphism in this way? So this picture give you some. So this is a morphism. Okay, this is a topological order of one dimension lower. You should always think about this something defined in a open N disk. Okay, okay. So similarly like that. Okay, but let's expand it a little bit. Let's expand it. Okay, this dot now become a line. Okay, so now you can see why it preserve algebra structures. So in this slide, I'm going to show you that this definition of morphism coincides with the mathematical notion of monoidal functor between two fusion n categories. Okay, why is that? Okay, think about the topological order. This is topological order A, and in this topological order, you can have a lot of topological defect. Okay, I'm only drawing one line. I don't want. You can draw a much bigger picture. Okay, but let me draw a codimension one defect. Okay, there are k codimension one defect. They can fuse along the line, right? So there is a monoidal structure between them, or algebra structure among them. Okay, so now you can see why. Now you can see why that definition works. Look at this. If you're familiar with it, you see this is sandwich. Okay, this is sandwich. Okay, why sandwich work? I'll tell you the original idea of why sandwich work. Because why sandwich can serve as a uh, notion of morphism? Because if you have a physical system inside, right, you want to have something preserve the algebra structure. So that means you cannot do anything violent to it. You cannot put a needle into the system. Then you break the local structure. So the idea is that uh, you don't uh, get into the system. You can only do some massage outside. That's the only thing you can do. Okay, but outside, what the meaning of outside? Outside this anomaly-free topological order is a bulk. So the only thing you can do is in the bulk. Okay, what do? You just insert another domain wall. Okay, and by inserting another domain wall, you can see immediately that by inserting a domain wall, by fusing this together, you got a B, right? Fusing this to you got a B. Clearly, this this like fusing another layer does not change the algebra structure. So A is automatically embedded in B by preserving the algebra structure. Okay. So mathematically, can make it very mathematically precise. For example, you want a morphism from A to B, right? Now in this case, I will replace uh, using topological order. Then I will replace A by its algebra by its mathematical description, which is given by a fusion n category. So now you consider what's the natural morphism between two fusion n category? Well, that's just monoidal function. So let's take fusion n category A and fusion n category B. Now we consider a very natural al uh, algebra homomorphism between those two. That's precisely a monoidal functor. Okay, a monoidal functor between A and B. Now we claim that this monoidal functor can be equivalent defined using this way. Okay, what is this way? Okay, it's equivalent to a domain wall between Greenfield center of B. So the bulk of B, in this case, is replaced by Greenfield center of B and Greenfield center of A. How to do that? Okay, this F is domain wall is defined by this category because B is there. If there is a monoidal functor from A to B, that means just think about algebra. If you don't familiar with category, just think about algebra. This algebra, there's algebra homomorphism. Once you have an algebra homomorphism, B become a module. Okay, A can act on B. So this F induces the A module map. Okay, so B can be viewed as a AB bimodule because A acts on from left and B acts from right. Okay, so B using this F, you got AB bimodule. Then you can define the bimodule maps from B to B. AB bimodule map from A B to B. But for this is for algebra, but for fusion n category, this become a functor category. Okay, and you can show that this functor category is automatically a domain wall between these two. Okay, and this two can go reversely. So if you have a domain wall F, you can define a fusion in this way equal B. Then F is automatically embedded to F. Okay, because F is automatically embedded into this. Because look, A is here, is automatically can be viewed as part of B. Okay, that's just the monoidal functor you're looking for. And this two construction is inverse of each other. So this is to demonstrate to you that this sandwich construction is indeed the right notion of morphism you're looking for. Yeah, yeah, yeah. You will see in the end because the description you described about the boundary it's gapped, right? Your case is gapped and it has a fusion category symmetry A, right? And you say its Greenfield center is non-trivial. How to fit in this case? Yes, I will tell you later. Because the what really happened is that what really happened that the Greenfield center hidden somewhere, and if you want a categorical description of that boundary of the trivial phase, right? Boundary of the trivial phase. If you want to have the precise mathematical description of the boundary phase, you need not only the fusion category, you also need let the fusion category enriched in its Greenfield center. Then altogether, this become a fusion one, become an enriched fusion category. Its Greenfield center is trivial. But most of physics literature don't talk about that missing one. But that missing one is exactly SymTFT. You will see later. Once you see the complete story, that problem will be solved. For example, I remember your question is very nice. I remember that in 2020 there is a meeting in Simon Center. Well, I didn't participate it, but Xiaogang sent me a video afterward. He said that Shao Shuheng asked the question, and that question relate to your question. So his question is the following one. Consider 2 plus 1D topological order, and you have a gap at the boundary. Okay. or gapless bond, doesn't matter. Okay, this is well set. Okay, this is well set up. But now you consider stacking CFT, stacking a CFT into it. Then become a puzzling. Why? Because CFT has a fusion category symmetry. Okay, you stack something, you change the fusion category symmetry. Why the bulk is unchanged? Did you see that? Because you stacking a CFT fusion category symmetry. It it should have a dream field center, which is not trivial. Where is that dream field center goes? Okay, yeah, it's exactly the same question, right? Exactly it's a similar question, right? Now this question will be completely solved in my talk eventually. Okay. We're not there yet, so I'm gonna tell you where that goes. So that's why we okay. So example. So let me give some example of the morphisms. Right. So did I convince you that this is the right notion of morphism? Oh, I want to give a remark is that people later on rediscovered the sandwich construction, and uh, and they find it very useful. So you probably wonder why they're useful, why they're so useful. You can use it to do everything. Yes, you can use it to do everything because this is exactly the notion of morphism between QFT. Using the notion of morphism, you can do everything. That's the secret behind all why sandwich construction is useful. I hope I already convinced you that this is the right notion. Let me give you some examples. Okay. So what are the morphisms? Okay, you can have identity morphism. What is identity morphism? Identity morphism is exactly the trivial domain wall in the box. Okay, because the trivial domain wall, because it's trivial, right? There's nothing in it. So you fuse them too. You don't change the A. You don't change the A. Okay. So this A is domain. This is codomain. Example two. Consider the trivial topological order, and A is non-trivial. Then there is always a canonical morphism between these two, defined by this. Okay. Here is completely empty. Remember, oh, okay, this dotted simply means this is completely empty. Just putting a dot there to show you there is something. Okay. But the trivial one. Okay. So this is trivial topological order. This is its bulk. Trivial trivial topological bulk is still trivial. Okay. Then you combine these two together, it's still A. This define a morphism from 1 to A. Okay, I'll give you a non-trivial one. uh oh, remember, yeah, that's a good question here. So I wanna so theta an is simply n plus one is tell you the dimension. This is n plus one dimension. If I reduce the n by one, simply mean this is a trivial domain wall. It's a trivial domain wall in anomaly free of order. Right? You can always view the trivial domain wall then by double folding it as a boundary to view it artificially view it as a one-dimensional lower topological order. Categorically, no, they're not true. No, it's not true. You want to understand it from categorical understanding. At this stage, there's no categorical, right? You want to understand in the categorical setting, then I would say that the fusion category associated to this it should be the fusion n minus one category, which is exactly the category of codimension one, codimension two. You see, this one form a fusion n category. All the topological defect inside this form a fusion n category. But if you restrict to the codimension, trivial codimension one domain wall, then the topological defect inside this is exactly the looping of the original one. So that means the topological defect in this dimension reduced the topological order is exactly given by the braided fusion n minus one category. Okay, if you want a categorical, okay. Then you can check that by by computing that dream field center, you get a double layer because itself is already uh, modular. It's already a Brady fusion, anomaly free actually. Okay, here is a non-trivial one. I already introduced the notion of by this dimension is n. Okay, ZA is n plus one. But if I reduce if I call it if you reduce the dimension by one, this refer to the trivial domain wall. Okay, this is trivial domain wall in the bulk. And there is a natural morphism between these two. So this is domain. I use the box to label the domain. You see the domain? Domain is A and ZAN. Trivial domain wall in the box. Okay. By stacking them, this is stacking, right? By stacking them, this define the domain. Okay. What 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 is the bulk of this domain? What is the bulk of this topological order? Is this one and this one and this one. Three layered. Three layered is the bulk of this two. Okay. And then how to define homomorphism? You need a domain wall between this three and the bulk of A, right? Because this is target. This is the codomain. So the bulk of the codomain is this. So this is domain wall between these two. Then this define a morphism. We're gonna use this morphism. Okay, this is not true one. Okay, let me make the statement. This pair, I already defined M, right? M is just this. M is this. Okay. ZAN is the trivial domain wall in the bulk of A. This pair satisfies the universal property of center. That if you want to more precisely, that means if X is another ND topological order equivalent with the morphism, okay, such that this triangle is commutative. Then there is a unique morphism from Xn to this one to the trivial domain wall in the bulk of A. Okay, such that the whole diagram commute. This is so-called the universal property of the of center. I want to give a small quick remark here. This is very important. Is that this? Oh, by the way, this is a morphism. Okay, it's a morphism between two topological order. So if you want a familiar situation, you can think about A as a group or algebra. It doesn't matter. Let's just think about the A as algebra. An algebra, there is a multiplication. The multiplication simply send A tensor B to M, right? M A, just simply AB. Just multiply this two. Okay, this is just ordinary algebra homomorphism. But in general, this map is not an algebra homomorphism. Why? This is the algebra. This is algebra. By doing the tensor product, they're algebra again. But this is also algebra. But this multiplication is not an algebra homomorphism. So let me write down the algebra homomorphism requirement. If M is an algebra homomorphism, that means you first multiply AB, then multiply CD, then multiply them together. You should compatible with first multiply ABCD first. Multiply ABCD. So there's the product is also algebra. How the what is the algebra what is the algebra structure of this tensor product algebra? It just multiply them component wise. So A times C, B times D. Okay, you got that. If you want this two to be equal, well, you check what is MAB? Just AB. What is MCD? Just CD. Here you got ACBD. You see the difference? The difference is that BC here. This is CB. In general, they're not equal unless AB is maybe A is abelian. Okay. However, if you replace one of them, for example, the C, okay, for example, the C, you replace if C is required to belong to the center of A, then this commute, right? Because C is the center of if C is the center of A, that means BC always equal to CB. Then this requirement it works, satisfied. So that means ZA tensor A as an algebra, this multiplication map from this algebra to this algebra is precisely algebra homomorphism. Okay. It's algebra homomorphism. So this is non-trivial already. So if you not using this picture, if you want to understand the picture using ordinary algebra, This is ordinary vector space, algebra, linear algebra over a vector space, then this is the center of A. And what is this M? M is exactly the defining multiplication. And this defining multiplication is very important. This M is an algebra homomorphism, very importantly, algebra homomorphism. Okay. In general, if you replace this by A, then this is not an algebra homomorphism. Okay. So yeah, this universal property simply says if X is another algebra, doing the tensor product, you have algebra homomorphism. This requirement is already very strong. It tells you that this is something that must map to the center. If you don't map to the center, it doesn't work. Okay. So this requirement already tell you that you have to map to center. That's uh how you understand the universal property of center. Yeah, I don't want to go to the detail, but really need a if you see this for the first time, trust me, you won't understand it in 3 hours. That's what happened to me, you know. The first time I was still a physicist student, my friends in the math department explained the universal property of tensor product to me. I listened for 3 hours. I feel like I understand every argument what he said. I still don't understand what's going on. It's this is the magic of category theory. Why this universal property already defined the mathematical notion up to canonical isomorphism is not some is something I never heard of. So I won't go through all the details here, but you have to trust me. Okay. So this already is already enough. This theorem, if you ignore all the detail, this theorem simply say the bulk is the center of the boundary. Okay. So you see in the SymTFT community when they use the uh, symmetry boundary on a gapped boundary, a topological boundary, and why the bulk is always the center of that is it's actually come from the theorem. Yeah, but Yunqing told me this is already so well established we don't even need to know where it come from. Okay, people use it. Okay, anyway, so that's where it come from. All right, so the universal property, why it's called universal property? Because all the notion of center are defined by the universal property. Okay, so once you know that something satisfies this same universal property, they're called center. If you run this machinery in the category of groups, okay, in the category group, and M is a group homomorphism, you recover the group homomorphism. When A is algebra and M is algebra homomorphism, you recover the Euro notion of center. Okay. When A is a fusion category, M is a monoid functor, it recovers Dreamfield center. If A is a braided fusion category, M is a braided monoid functor, it recovers Muger center. They all called center. Okay. Also, the center of open string CFT is a closed CFT. This is called full center because they all satisfy the same universal property. Why they're called center? Well, because the same universal property. More generally, you can, if you were in a mirror symmetry, you probably familiar with this. Generalize the link conjecture. The En center of En algebra is an En plus one algebra. Okay. Well, this result immediately have a lot of consequences, but this slides give you a little bit historical context. The first discovered uh, boundary bulk relation, you know, the bulk is the center of the boundary, is in 2 plus 1D, non-chiral topological order. The non-chiral simply means topological order meet gap the boundary. And we have recovered the well-known result. In this case, in the 3D topological order can be described by a modular sensor category. Okay, so the bulk is given by modular sensor category, and its gap the boundary is given by the fusion category. And their relation is that the dream field center of the fusion category have to be the bulk. Okay, so this is the fusion category. This is fusion category. The fusion they have they could be different fusion category. There are three different fusion category. If they share the same bulk, that means they share the same dream field center. Okay, their bulk is always the same. So they are different boundary condition of the same bulk. Okay, and between them, you can even see more structure between them. It's shown that if they share the same dream field center, they're Moretti equivalent. Moretti equivalent, that means the domain wall between these two are defining a invertible bimodule. Because look at the domain wall. If this is domain wall, L axon from left, M axon from right, so it's a bimodule, and this bimodule turns out to be invertible. Okay. according to Adingov-Nikshi-Gostrick theorem, two fusion categories are Moridi equivalent if and only if they have the same center. Okay. Now we want to generalize this result. Well, still looks very, this is already very powerful statement. Okay. But I think the next statement is not so familiar to this community. Now we consider more. We consider a topological order with a gap boundary, another topological order with a gap boundary, another topological order with a gap boundary. Okay. But these three are different. So if you want to connect them, you have to use a domain wall. Okay, connect them. Of course, here you also have domain wall to connect them. Consider this physical configurations. Okay, it turned out that this L determine the bulk, as we have shown before. M determine the bulk by taking the dream field center. N determine the bulk by taking the dream field center. Not only that, they have a domain wall, right? L, M, X on this from two sides. So X, it must be a bimodule between these two. But previously I said this is invertible. I said this is invertible because there's no bulk. They're all the same. But now the situation is slightly different. X can have a non-trivial bulk, relative bulk. Okay? It turned out that X also uniquely determine this. Y also uniquely determine this. Okay, you can even compute what this domain wall is. This domain wall is exactly the functor category from X to X, bimodule functors, because this X have a left L actions and a right M actions. Okay, so bimodule functor define a well-defined fusion category, and this fusion category turned out to be a well-defined domain wall between these two. Not only that. You look at this picture, you immediately can ask the following question. What if I fuse them together? Okay, if I fuse them together on the top side or on the in the bulk, you do the following fusion. Okay, you do this fuse with this along with the dream field center of M. Okay. On the other hand, this also fuse with that, right? X also fuse with Y along M. Now the question is, after fusion, do we also determine the relative bulk as this side? After you fuse you got this domain wall, right? You got a relative center. Okay, you got this one. Does this two equal? Yes, they're equal. That means this assignment is functorial. You know what I mean? This consider an object in the category. This consider a one morphism in the category. So the object is mapped to the dream field center. Okay, the morphism is mapped to a relative dream field center in some sense. Okay. And this assignment is functorial because you can compose the one morphism here, then map. Or you can first map them individually, then compose. They are compatible. So this simply tell you that this assignment is a functor. This defined functor called center functor. Okay. This is not so familiar to literature as far as I know. This functoriality become very important formula for computing the sandwich. You see, that's why we didn't draw the sandwich. So Xiaogang said, well, this picture looks like a taco, but it never got popular. I never use taco. I feel like we're Chinese, right? I think about this as a fence, right? It just look like a fence, you fold it or unfold it. But you always draw, you don't look, this is a sandwich, right? If you forget about this part, this is a sandwich. But we always draw the little corner in the between because it tell you how to compute it. So here is the idea. For example, why this formula is become a fundamental formula to compute the sandwich. Look at this. For example, think about the special case M equal trivial, right? Look at this. Uh-oh. Is that a good idea? No, no, no. I want to consider, sorry. Oh, maybe uh that's not a good idea. But this formula immediately give you how to compute the sandwich. For example, consider this is a sandwich. If I cut this part, it's a sandwich. Can you see that? Okay. It's a sandwich, right? So when you fuse sandwich, how to compute the result? Okay, the idea is very simple. If you allow to add this dot, then you can compute the sandwich immediately, very easily, because because taking the center is a center is functorial, right? By fusing this two is equivalent to just fusing this two. You simply got that. But remember, this must be the center of X, right? This must be the center. What's the center of X? This is functor X to X. Okay, that's the notion, the meaning of center functorial. So this formula immediately give you this formula. Okay, it's not so easy to see how. I'll give you another example from physical context. This become more frequently used. Think about the Dagor-Witten theory. Or if you can ask matter physicists, you think about the quantum double, GitHub quantum double model. GitHub quantum double model, there's two gap the boundary. One is called RAP-G, okay? Some people call it smooth boundary. And we call this or rough boundary, whatever. And connecting them is invertible domain wall, which is given by back. Okay. Now you ask how to compute, how to fuse them together. You're gonna use this formula. This formula immediately tell you the result. By fusing them, right? By fusing. Well, if you compute the fusion in a bulk, it's difficult. You know, what this formula tell you? Fusing in the bulk is difficult. Don't do that. Do this one. This one is easier. Okay. So, but this one, you see, after you fuse them, this become a vect. The functor from vect to vect is still vect. So that means you fuse them, everything becomes trivial. This has been used in the SymTFT literature very often. But what I'm trying to tell you is that this formula is the underlying powerful tool, allow you to do the fusion of sandwich. Okay. I didn't hear it. Can you say it again? Can you ask again? Direction of the morphism. Ah, um, well, I didn't mention that, but oops. But it's you mean for this one, you want to treat whether it's a morphism from L to M or M to L. Well, you just choose a consistent convention you wanted. Then should be okay. We always choose carefully what's the convention we use. Yeah, in the paper we go. But sometimes we switch. But we'll be consistent in one paper, you know. Yeah. I couldn't tell you. But most of cases we will treat everything going this way, going this direction. Yeah, in most cases. All right, I'll tell you another result. This functor is not only a well-defined functor, it's fully faithful. It means that X uniquely determines the relative bulk. Not only that, the relative bulk is also uniquely determining the X. Then this functor is fully faithful. How to see that? This is quite magical. I'm going to show you the proof in one line. The proof is just in one line. Okay, what is this X? X is Lm bimodule. Lm bimodule can also, you can do the double flipping, right? You can do the flipping, they become L stacking a M reverse left this module over. Okay, X can be viewed as a module left module over this fusion category. Okay, but X is a module over that. What does this mean? This just means there is a monoidal functor from this to functor XX. It's just another way to represent the a G representation or KG module. This is equivalent. But remember what I said before, there is a theorem we have an equivalent way of defining monoidal functor, right? From one fusion category to another fusion category. What's that equivalent definition? You have so a monoidal functor from this to this is equivalent to give a bimodule between this and the trivial phase because the trivial center of that is trivial. Okay, a domain wall between this topological order and the other topological order, trivial topological order, this is domain wall. Okay, by fusing them together, you got this. So what does this mean? This means a monoidal functor from this to this is exactly given this line as another boundary of this. And the proof is done. Because this is just translation of language. Given a bimodule, given a LM bimodule is equivalent to give a monoidal functor. Well, given monoidal functor is equivalent to give this domain wall. You're done. Okay. This one-line proof actually highly non-trivial because this result, when the center functor is fully faithful, imply the following result. AB Morita equivalent only if the dream field center is trivial. Moreover, the broad Picard group of A is equal to the braided autoequivalence of the dream field center of A. This is two fundamental results on the fusion category proved by Eddingov, Nixie, Gaustrich. Can all be summarized into a physical statement of boundary bulk relation, or the center is functorial. Where did we use and what's your question? Sorry, where did I use it? What? Oh yeah, this one. Yeah, but for higher, there is an issue. Higher, for higher dimension, you can have a gap domain wall here, but this one is gapless. You can, for example, you can have the situation like this, right? You stack a lower dimensional topological order into it, you won't change the bulk. So higher dimension, there is a big issue. But thank you for asking the question. If you want a higher dimension generalization, this is given by here. I won't go through it. Okay, it tell you how to characterize this non subjectivity and the non fulliness and the non faithfulness. Okay, there is a precise characterization of that. Okay, I won't go through, but so you can. But this tell you that you can do a lot of things about the center functor. It summarizes many results in the field actually. The formal proof of boundary bulk relation assume only the well-definedness of the notional morphism between two quantum phases, which is further based on the uniqueness of the bulk and the well-definedness of the fusional domain wall. This notion and formal proof should be worked for certain nice gapless phase. So as long as all the you see the argument is very easy, very general. As long as all the argument went through, um, you can consider phases in a very general setting, as long as it's guaranteed the proof work. Okay, then it holds. So for rational CFT, you can do the similar thing. Because in that case, you can, I don't know whether you know it. So it's well known in the rational CFT that the closed CFT is also the center of the boundary CFT. Okay, it's something similar. So because of that, we give a name for those quantum field series such that above formal proof of boundary bulk relation work will be called quantum liquid. A notion, yeah. If you want to understand from the QFT, you can be viewed as a notion can be more precisely defined as a fully dualizable QFT. For the time being, let me skip it. Okay, so let me give a short remark. This will be too long. I want to give a short remark is that in the Euro sandwich setting, this our proof definitely our proof start with the gapped topological order in the box, and this is gapped, and this is also gapped. But if you change one side to be gapless, this definition work perfectly. Okay, look at this. If you replace A by something gapless, this definition works perfectly without any problem. As a consequence, this also works without any problem. So what does this mean? This means the bulk is the center of the boundary. Even when the boundary is gapless, it still works. Okay. So this become a guiding principle here. So well, you can use that to lead to a classification of anomaly topological order up to invertible one by fusion n category with a trivial E1 center, or Brady diffusion n category with a trivial E2 center. That's you can use the bulk equal to the center of the boundary to obtain a classification result of topological order or characterization of topological order. But what is important to us is the following one. The proof also apply for topological order in the bulk, but with a gapless boundary. So when this one is gapless, okay, it still works. As a consequence, when this is gapless, its bulk have to also be dream field center of A in some sense. But this A cannot be the ordinary one. So when you ask me the question, what if I put a anomaly free one, but that anomaly free one contains a fusion category symmetry? What the bulk is trivial. If you consider the dream field center of the fusion category, it's not trivial. What's the problem? There's something that means there's something missing in the description of the lower dimensional theory. Uh, Now I'm going to tell you what it is. So in that case, you have to when the system contains a symmetry or contain a gapless quantum field theory can also be viewed as something with a symmetry. In that case, you have to replace the fusion category by an enriched fusion category. That will solve the problem. Okay, I'm going to do it now. Since we already have a precise categorical description of this one, so this suggests something very powerful because this one tell you we have a mathematical description of the bulk. Okay, as a Brady diffusion N category with a trivial E2 center. Then we can find the categorical description of the gapless boundary by solving the mathematical equation. You cannot assume what the question mark is. Well, definitely question mark contains some kind of a fusion category structure, but it's much more than that. Okay, you cannot use this to be a fusion category. Your question exactly, oh, what if I replace the question mark by fusion category? Then it's dream field center. Well, oh God, it will have nothing to do with it because in your case is that C is trivial, right? Consider trivial bulk. Okay, then what happened? So I'm gonna solve this in today's talk. So let's consider 1 plus 1D worksheet of a gapless boundary of 2 plus 1D topological order. Let's consider that. What happened? Well, let me tell you that the first time we noticed that when Zhenghao and I noticed that we're shocked. Why was shocked? Because gapless phase is always hard to me. Very difficult. We don't touch upon it. We don't really deal with it. But after seeing that this bulk is the center of the boundary, when the boundary is gapless, it simply suggests to you that there is a unified mathematical theory for gapped boundary and the gapless boundary. Okay. Now we just try to solve this equation. Before we try to solve the equation, what does question mark have to be? Well, when when this is gapped, what does question mark really be? If this is gapped, we know that this question mark have to be a fusion category. Okay. So when it becomes gapless, what's gonna happen? So we for the fusion category can be viewed as a observable macroscopic observable or observable in the long wavelength limit. So when you consider gapless phase, you gotta do the same thing. So the question becomes, what are the microscopic observable on the 1 plus 1D worksheet? So we have to analyze that. So let's consider most general situation you can have. On this worksheet, we know, let's say when the gapless boundary is given by conformal field theory, on the worksheet, you can have some OPE, right? You have some OPE field. People know that you gotta have a VOA somewhere. Okay, but VOA is not enough. Okay, I'll tell you the VOA is totally not enough. You need to add all the topological defect lines. Okay, so in general, what do you have? You have a set of labels for topological defect line. Topological defect line, I would simply use TDL to denote it. So you got a bunch of label ABC. This ABC label the defect line. Okay, and you have MAB. Okay, between two different defect line, there is a defect junction. That's the most general situation. Okay, on each defect junction, you have a space of field leaving on the junction, leaving on the 0D. This is space-time dimension, defect junction. This is infinite dimensional. Okay, there are infinite dimensional fields in leaving it. Okay, in particular, it means that the space of field leaving on the TDL is simply labeled by MAA. Okay, what is MAA? B become A. B become A. Well, it's just junction on itself. So the field on the TDL is a special case of MAB. Okay. Now you can consider OPE. OPE on the defect line, right? There is field leaving on the defect line. They can do OPE. Okay. Field on the defect line can do OPE, but this is not the most general OPE. The most general OPE is that you have a defect field leaving on the defect junction of MAB, and you have another defect field leaving on the defect junction MBC. Now you fuse them doing a OPE, it become a field living in living in the defect junction between A and C. This is the most general OPE you can have. Okay, defect junction fusing. This summarizes everything almost. Okay, but you can see almost immediately that oh, this looks like a categorical structure. What is the category? Category is just a bunch of label, and for each pair of label, you assign harm space. But look at this. This for each label, for each pair of label, you have a space of defect field. This is infinite dimensional. Okay, we will show that this structure, this composition called OPE, actually define a B enriched category. I'm gonna tell you what the B is. A and C is not joined together. Yes. Oh, MAC that you you have a field, you push them into a small distance, they will have OPE. That's what I mean. Even the A and C are not connected. In some situation, you can have a MAC equals 0. That's allowed. Because I didn't tell you, oh, this is space. What if the space 0? Oh, that's possible. That's possible. Yeah. So this will be boundary. To be more precise, this terminology is slightly. These are space of chiral vertex operators. But the chiral vertex operator living on the boundary of CFT is called the boundary changing operators. Yeah, but here you don't even have a boundary, so you have a line, right? Unless you do a dimension reduction, because I didn't draw the bulk, I only draw the boundary. A boundary, 1 plus 1D worksheet a boundary, but you also have a bulk. But if you squeeze bulk into a one-dimensional lower, this line, along this line, for example, you fold in this way, I draw this in my some other talk, so I didn't draw it for this talk. So if you fold this way, you fuse everything in the bulk, 2 plus 1, 2 plus 1D bulk into a 1 plus 1D, then this become a boundary set. In that case, you can claim very precisely without any ambiguity, MAB is precisely a boundary changing operator, space of boundary changing operator between two boundaries. Okay, now we give a little more precise analyze. Among all the label, there's a trivial one. Among all the label, there's a trivial one. I'll denote as a one. It's a label for the trivial TDL. What is the meaning of trivial? For field leaving M11, remember that we have, right? For all of them, you have M11. When one is trivial, you also have M11. Okay, what is M11? Because, well, M11 exactly the field leaving the two cell. Why is that? What's the meaning of a TDL is trivial? A TDL is trivial simply means it cannot be distinguished from its neighborhood, right? It cannot be distinguished from its neighborhood, then M11 is precisely the field leaving the neighborhood, leaving the two cell. Okay? Okay, this is the field leaving the two cell, and you can see immediately that this M11 have to be a VOA. Because leaving the two cell, you cannot have a multi-valueness. Oh, let's assume it's chiral. Right now, I didn't even assume chiral. Assume it's chiral, then this M1 might have to be a VOA. That's a remark. I didn't assume it right now, okay? You could have a non-chiral, okay? A subalgebra field generated by energy moment tensor is transparent to all the TDL. This is definition of minimal definition of TDL. What is the meaning of a TDL? TDL is that uh, uh, the minimal requirement is conformal invariant. What is the meaning of conformal invariant? The meaning of conformal invariant is the energy moment tensor. The subalgebra generated by energy moment tensor should be transparent to the TDL. That's the minimal requirement for a defect line to be conformal. Of course, it's also a minimal requirement for a TDL to be a tautological. Okay. But in general, this is a minimal requirement. Without the loss of generality, we can assume that in between the minimal choice and the maximum choice, there is an unknown V such that it is transparent to all the TDL. So that means I already define my TDL as V invariant TDL. Let's assume that because I don't know what the V really is, V will be eventually become a defining data of my theory. Okay. But I didn't require what the V is. V could be this, could be this. I don't know, but just give a V a name. And for convenience, actually, actually, the next statement can be relaxed, but just for convenience, let me assume V is a rational, just for convenience. V is a rational, then mod V is the category of V module is a module tensor category. This is conjectured by Morphism, which one of the crowning achievement in the field of VOA, proved by Yizhi Huang. Okay, it's a theorem now. Okay, let's assume that. Okay, then as a consequence, what does this mean? That means V is transparent on the entire worksheet. Okay, that means MAB is clearly a V module because V acts on this. Not only ordinary V module, it has a two-dimensional V action. That means V can fuse onto the defect junction in one along the line. You can also rotate it along the defect junction for 100 times, then X. It makes no difference. So so MAB is clearly has a V action of two-dimensional V action. This is precisely the definition of a module over VOA. A module of VOA actually should be usually called V2 E2 module. Okay. So MAB is clearly a V module. Okay. A mathematical denote has that. Secondly, there is a compatibility between the OPE. Remember, we said that there is the most general OPE is that to fuse the defect field here, fuse with another defect field here, you do OPE. We got that. This is very complicated. Remember that this is tensor product is a over complex number. So this is highly non-trivial. This is a V module. This is a V module. By doing this tensor product, it's not a V module anymore. This is a V tensor V module. It's not a V module. This is very important. So this is not a V module. This together is not a V module. This is a V module. So you cannot claim this is a V module map. No, you cannot claim that. So this is the subtlety of the VOA theory. It's the intertwining operator. You do it more carefully. Okay, the compatibility of this OPE and the V action. What do I mean by that? I mean the following. Because V looks like a transparent everywhere, then you can fuse the field in V onto this MAB first, then fuse with field leaving in MBC. Or you can do fuse V with field in the MAB first, then do the fusion. Or you can fuse this two first, then let V act. These three different way of doing it exactly defining property of the intertwining operator in a view. So as a consequence, this compatibility exactly translates to the following statement. Now replace V by V module, relative V module. Then this is V module, this is V module, relative over V, still a V module. This is also a V module. Then it's legitimate to say there is a morphism between these two. Okay? A morphism in the mod V. So now I translate the very complicated compatibility of this OPE with V action into a precise mathematical statement between two V module. A morphism between two V module. What does this mean? This means that this morphism is living in mod C, mod V. Mathematically, it means that it defines a composition. It defines a composition in the mod V. As a consequence, we obtain a mod V enriched fusion category. This mod V is exactly what is missing. In the case you're considering, S is the fusion category, and the mod V is string center. Okay, so observable on the space-time on the boundary, the worksheet of the boundary is exactly given by an enriched category. If you require the bulk to be trivial, then mod V have to be the dream field center of S. The dream field center of this enriched category is trivial. Then there's no ambiguity. There's no contradiction. You see what I mean? Yeah. Well, most of physicists don't have that. Okay. All right. Now I will tell you this statement. The rational, because we assume the rationality, okay? You can drop it for a certain reason, but I will tell you later. So a gap, the gapless boundary of 2 plus 1 topological order can be completely characterized by a triple, okay? Where V, for a chiral gapless boundary, V is a rational VOA of central charge C. For a non-chiral gapless boundary, V is a rational full field algebra. The full field algebra is a non-chiral analog of VOA, okay? Non-chiral analog VOA, such that the left mover, the central charge of left mover, subtract the central charge of right mover equals C, okay? What if when V is trivial, it describes a gap boundary? So this mathematical theory unified gap and gapless. And S is a fusion category equilibrated equivalence. This C is I don't know how to fix it. It's not a typo. I tried it almost 1 hour to fix it. I couldn't. It looks like a bug in my in my tech shop. I have no idea what's going on. Okay, this is C. Okay, this is C. C is this one. This one. Okay. There is a braided equivalence of that. Okay, because there's a braided equivalence, so that means mod V acts on S. Okay, mod V is a part of the Dreamfield center of S. Okay, so as a consequence, it acts on S. Acts on S as a module. So we define, so we can set B equal to that. B equal to that. So B acts on S. Why we give this a new name? Why we give it a new name? You will see it in the next slides. Okay, we simply give this a new name. We didn't do anything new. Okay, just give it a new name. Then B acts on S. There is a canonical construction. There is a canonical B is a braided fusion category. A module actually B is a modulus category. S is a fusion category. B acts on S. Then there is a canonical construction called canonical construction using internal harm. Okay, unfortunately, I won't talk about the detail, but this is very important. So there is a canonical construction because B acts on S to define MAB. Remember what is MAB? MAB is exactly all the MAB is exactly. So what I'm trying to say here is harm AB is by definition the internal harm of is the object in B. Is an object in B, okay? Is an object in B. The internal harm is the object. It can be computed precisely. Okay. And an upshot here is that you can Bach is the center of the boundary. You compute this, the center of the enriched category, you get the Bach. This condition looks a little technical. I'm gonna unravel this geometrically for you. Okay. So this theorem simply says, let me restate the theorem. Okay. This theorem might look technical to you. Okay. Let me restate the theorem. So this theorem says that, okay, so to describe a gapless boundary, gap or gapless boundary, you can describe by a pair. This pair contains two set of data. One is called local quantum symmetry or dynamical data containing dynamical information. The other one is purely topological. Remember that the B, what is the B? B, well, you can define B using S, but B is a mod V, right? B is a mod V. We intentionally give it a new name. We intentionally give it a new name because I wanna separate. I don't want to talk about the mod V. I want to separate the topological data from the dynamical data. Look at the topological data. We call it topological skeleton. Okay, this topological data can be obtained by a topological weak rotation. That is precisely the physical meaning of this technical condition. Right. This technical condition now becomes the following. How to determine this topological skeleton? Consider the following situation. You have a topological order BC. This is a chiral central charge. This is a modulus category. Another modulus category in C, okay, with the same C. Assuming that they're with equivalence, that means that there is a gap domain wall between them. Okay, this is a well-defined situation, right? Now you do a magical rotation. This is in the spatial dimension. This all I only draw the spatial dimension. Now you rotate this to a vertical direction, pretending that is in the time direction, pretending that is time direct is a virtual or fictional topological order, leaving in the time direction. And the whole meaning of the putting them vertical is because I want to combine B and S. Now I replace B and S by an enriched category. This is topological skeleton of a gapless boundary. And its dream field center is the bulk. Again, you got the center of the boundary equal to the bulk. For most of physicists, now people talk about topological holography. They're talking about this case. When C is trivial, what if C is trivial? Now this is gone. You only have this part. Now you make them look like vertical, and this is gone, right? You got a BS. In this case, B have to be the center, dream field center of S, right? Because look at this. Look at this. C is trivial. Assuming C is trivial, then this is gone. Then this is B. B is the dream field center of S. That's exactly the dream field center you asked me. Where this dream field center goes. So when in that case, so let's consider C is trivial. Consider did I have the oh no. Oh, I don't have. Okay. So for most of physicists, when they talk about the gap in space, they don't talk about the B. Okay. They usually don't talk. They only talk about the S. Then there's a question: where is the central center of S goes? They use the sandwich construction because I will show you the sandwich construction. It's not so convenient, but it's durable. Maybe we should do that. Okay, let me just show you this. Okay, let me just show you this. Okay, because this side is gone. So this is a few. Well, I generate to a higher dimension already. Okay, this become a fusion n category. This is dream field center of that. Now you do a topological weak rotation. You got a one-dimensional lower theory, which potentially could be gapless. Could be gapless or could be gapped SET, SPT. Okay, you have that. Okay. Now, according to us, this already represents a gapless phase. Okay, it's quiche. It's precisely quiche. If you want to expand it as a sandwich, that's fine. You just drag this to the side. Now this become your SymTFT. Okay, this is your SymTFT. This become a canonical gapless boundary. But remember, what is canonical gapless boundary? You have a dynamical data, and you have a enriched diffusion category given by the dream field center of S enriched in itself. This is precisely what the physicists had in mind when they talk about splitting of a gapless phase into a sandwich. What they really mean is that, oh, this part catch all the information of symmetry, and here's the same TFT, and here is all dynamics. But that's not precisely. It's not that on this side only you only had dynamics. No, you also have topological data. Okay, except that this topological data, is sort of canonical in some ways. It's compatible with this. You know what I mean? Is the SymTFT enriched in itself, but it also have dynamic data. This is what essentially they had in mind. Okay. But our theory also tell you that, okay, if you're given a theory like this, do you have other splitting as a sandwich? Yes, there are infinite many of them. You can characterize all the sandwich construction by a functor from any fusion n category to S. As long as you have a functor, you have a sandwich construction. But among all of them, there is a canonical one. The canonical one is just identity functor from S to S. That's exactly give you the sandwich construction. Okay. Remember a functor, just a sandwich. Right? Sandwich is a morphism. Okay. So, but from us, there is a reason not to expanding this because it's not so convenient from us. That's why we didn't call it sandwich construction. Because there's a good reason for this is that because this is already a quiche. It's already a quiche. You don't need to expand it into sandwich. There's a reason you're not to do that. So I will tell you the reason. Because I want to do the weak rotation. So now I can have a topological order 1, topological order 2, and they have a different center charge. That means they're not living in the same weight class. then the domain wall have to be gapless. Domain wall is gapless. According to our theory, you can have a virtual topological order in a vertical direction. Okay, is given by this pair. Okay. Similarly, from D to E, you see the central chart doesn't match. Central chart doesn't match. That means you also necessarily have a gapless domain wall between these two. Because it's gapless, according to our gapless theory, that's equivalent to have a virtual topological order leaving on the time direction. Why you want to do this vertical thing? Why we call it topological? Because of, I'm going to show you why it's so powerful. Do not use the sandwich. Using this, it becomes much more powerful. Because when you do that, this is gapless, this immediately give you a way to fuse them. This is the gapless domain wall, right? This is the gapless domain wall. You see that? You see that? Okay. How to fuse them? Well, look at this picture. Because I rotated a fictional topological order into the time direction, just pretending they are the true one. Pretending they're the true one. How you fuse them? You fuse them component-wise. This is some local data VOA or non-chiral analog of VOA. You fuse them, you just fuse them as a over C, right? That's obvious. And what is A? A is in the time direction, right? B is in the time direction. What are you gonna fuse? How are you gonna fuse this to? Well, you just fuse them component-wise. A fused with B. A fused with B. Now, in the base, there is M, there is N, there is a D. How you fuse them? You fuse M with N along D, right? Okay, you fuse them. That's almost tautological. This is the fusion formula. Almost trivial, but actually it's not trivial. Why? I'm going to show you. Become highly non-trivial. Consider 2 plus 1D topological order with a canonical gapless boundary. Canonical gapless boundary simply means C enriching C, and C is precisely mod V. Okay, let's consider this case. Okay, this is a canonical boundary. This is a canonical boundary. In the middle, I will insert a domain wall M between CC and CC, gap domain wall M. Okay, according to our formula, right? According to this formula in this picture looks very naive, very trivial, just fuse component-wise. Okay, you do the same thing. You fuse, right? This vertical one always represent the gapless phase, represent the gapless boundary. This also gapless boundary. On the one side, they move in this direction. On the other side, move this direction. But when you fuse them, you have to flip the orientation. Okay, this is the VV, okay? Because the orientation go this way, right? Yeah, like a circle, right? Going this way. But if you want to flip this, you have to change you have to change the V to V bar. Left mover become right mover. Okay. So V become reversed and that become C bar. This C bar exactly is the one that changing the braiding to anti-braiding. Okay. Now you use that formula. You do it naively, you got that. Looks pretty naive, but it turned out that M11, M11 is the internal hum of 1, inside the CC bar. CC bar is this one, canonical construction. This recover all modular sensor category in rational CFT. All. There's no, because all the modular invariant 1 plus 1D rational CFT can be obtained in this way. Let me say more. This actually provides in the mathematical theory of conformal field theory, there is a mysterious relation have been noticed a long time ago. Modular invariant CFT extending a VOA pair of VOA, okay, is exactly equivalent to Lagrangian algebra in C box and C bar. Okay. Well, this theorem we proved it in 2008 actually is before the Lagrangian algebra was invented. So this notion already found in there, but it's not called the Lagrangian. The name was coined by other people like Muger and Davidov and Ostrich and Nikschik in 2010, I think. Okay, but that point is this already proved without giving a Lagrangian algebra, without the name. And also know that the Lagrangian algebra is a one-to-one corresponding to the gap boundary of that. And it's also known that it's equivalent to the gap domain wall. between C by using the folding trick. And more than 10 years ago. No, no, no. More than 20 years ago. So, around this period of time, people uh, puzzled about this result. Why? Because there looks very mysterious. Now there is a simple explanation. You see, M here's domain wall. You fuse them, you got that. And how you compute the partition function living on the two cell. That's just M11. M11 just internal Hom. You compute the internal Hom, you get a partition function. Not only you can get a partition function, because M1, remember this is M11, you can get all the TDL. If you want to know the partition function of all the TDL, this is a simple formula, just MAB. MAB is internal Hom, it's still internal Hom. So this formula, but what internal Hom? You need to know this category first, okay? But this category is obtained by previous fusion formula. It's given by this formula. Okay, once you have this category, you have this category, you identify each object, which object you want to compute, you compute the internal Hom, you get a partition function. This is automatic, okay? So this formula is already containing all the partition functions of TDL. For example, you have a TDL here, right? You have TDL here, you have TDL here. You fuse them, you want to know what's the resulting TDL, what's the partition on the TDL. This formula already automatically give you this result. Automatic. Because I think Zhenhao and I first developed the theory. We're kind of in a disbelief because could that be just as simple as that? Yes, it's just turned out to be the very simple. So all the modular invariant partition function can be recovered from this way, uh, by choosing different domain wall between M. Okay, so that's already covered in this. All the modular invariant just is one-to-one corresponding to gap domain wall inside it, inside the C. Okay. Um, there are a lot to be said, but I think my time is 3:30. I still have some example I could explain, but I'm not sure. But I said, this skip unless people ask questions. Yeah, 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 yeah. I can summarize the results so that yeah, if you want to know the more example, I could tell you. So let me summarize the result. Okay, so the most general topological weak rotation also tell you the most general holography is the following one. You consider domain wall or between two topological faces in any dimension. Okay, any dimension. Now you rotate one of them to the vertical direction, pretending that this is some virtual topological order living in the time direction. But what basically really mean is that you have to combine the topological data here and the topological data here to give enrich the higher category such that this characterize the topological data of the boundary. So this boundary could be gapless. Okay, this could be a gapless boundary of a general topological order. C could be a topological order of any dimension. Okay, so that's why it's called a potentially gapless boundary of n+1d topological order C. Okay, how to obtain topological data of that? Just doing the same trick. Okay. In physics literature, they usually don't consider this, but for people from Oxford, they rediscover this result in 1+1. It's called a club sandwich. They call it club sandwich. Okay, but anyway, um, okay. If you don't use the class sandwich, you can make it more precise. Just forget about the other side. You just want to using this. You rotate it to time direction. You got to enrich the higher category. You can make more precise statement of this. So it's a topological order with a gap boundary. On the one side is S is the category of topological defect on the boundary, and this is dream field center. It's a category of topological defect in the bulk of codimension 2, actually, to be more precise. Okay, and this is naturally acts on S. On this side, what the dictionary is, S become a category of topological defect or super selection sector of state. And the trivial center is category of topological sector of operator, slightly different. Okay, it's space of non-local operator invariant under the local operator algebra. Okay, clearly this also acts on that, so it's slightly different. Okay, this is the dictionary. Um, there are a lot more to say about this, but I already explained this relation to SymTFT, right? Yeah, just is actually a quiche if you rotate to the vertical. So I said why we didn't call it the SymTF. We didn't invent the name of SymTO or anything because we feel like this topological weak rotation is more fundamental in general because you do that, it provides a fusion formula for you, right? As I explained over here. Uh, it gives you how to compute the partition function of any topological defect line. Okay. That's the one of the this is still the one of the reasons why we call it topological research. There are some other. Okay. For example, you can do the topological research not for one phase. You can do this for all phases. Let's consider the space dimension. So first, you can consider this a space dimension. Okay, this is topological order. This is gap the boundary of that topological order, gap the boundary, and the domain wall between them is the relative domain wall. Okay, so on and so forth. Okay, you can rotate the whole thing into the time direction. You take the whole thing into the time direction. Now you obtain what? You obtain the topological data of all quantum liquid. One of the most amazing result in this direction is that if you denote the category of ND anomaly-free quantum liquid, okay, that's already included rational CFT. Morphism are domain wall. Now domain wall is this pair, okay? Now if you rotate it to the time direction, this pair represents the topological data, topological skeleton of a quantum liquid. This pair represent the topological data of quantum liquid. And this pair represent its domain wall. Okay, because everything is this determine that, this determine that, this determine that, this also determine that, this also determine. So only thing you need to care about is this dash box if you want to compute the category. It's turned out that the category liquid is equivalent to the category of topological data, and topological data can be computed very, very easily. This is surprising. This almost looks like a serial everything, but what's this? This looks almost trivial. What is the n plus one vec? N plus one vec is defined by Gaiotto and Johnson-Freak. It can be defined from complex number. Given the complex number, you do a magical thing called the looping. You do it do it iteratively. So it's not something very crazy. It's something can be computed very easily. Not very easily, but can be computed. Okay. Only thing you need to know is about the complex number, starting point, the complex number, and this dot is just a dot. No specific meaning. So this is quite trivial. This is quite surprising to us because n plus one vec is nothing but the categorical description of trivial n plus two topological vector topological orders. Trivial topological order. Why this thing happens? The main picture is this. Consider a trivial topological phases, trivial topological order. You want to find a mathematical description of it. You have to including all the non-trivial quantum field theory in the lower dimension. A trivial topological order contain all the non-trivial quantum field theory living in the lower dimension. So it's highly non-trivial. Okay. Let me use so the theory of everything become trivial. This remind me of something, in Buddhism. I have to use the Chinese. I don't know whether it's called the 色不异空，空不异色. So the emptiness is everything. Let me translate it. That means, and the emptiness is everything. Everything is emptiness. That's exactly the statement there. Okay, so I think that this is the most striking result in our theory, one of the most striking results. Okay, to summarize the notion of morphism, we use that, and use that we derive the bulk is center, and we also tell you the bulk boundary bulk relation is functorial, it's got the center functor, and we also derive the topological weak rotation. Okay, a few more guiding principles. You add them up, you can make up the full story of this. Okay. Okay, so the last conclusion is that if the notion of morphism is arguably the most important concept in mathematics, it's only reasonable that it become a notion of morphism of quantum field theory is an important concept in physics. Okay, thank you very much. Yeah, yeah, yeah. No, no, that's not what I mean. I think you can definitely compute without my theory. You have a fusion, two fusion category. You want to compute with a bimodule. But what I mean is the following one. So, um, okay, let's say here is A. Um, Here is a bimodule. Here is a B. Now you have a A. You have a B. If you have a situation like that, our formula tell you that how to fuse A with if they share the same dream field center. Okay. Our theorem tell you this to be functor M to M because to say M is a bimodule is equivalent to, well, I'm cheating a little bit. I'm cheating. This is a what I'm saying is that um to have a bimodule A B bimodule M is equivalent to have A tensor B relative to A is equivalent to have A box B reverse to functor M to M. Then a functor from this to this can be is equivalent to add a domain wall here. This domain wall is precisely the relative bulk of M. Okay. So that's why you see we don't draw sandwich. We always add something because that help you. So we always so people draw this a sandwich, right? But we always like connecting them in at the bottom because that tell you how to compute the sandwich. Yeah. Yeah, it's give you a very powerful compute a method of computing it. So a lot of people will say, oh, what if you add a invertible domain wall? Well, that as a sandwich automatically give you a duality, right? Invertible domain wall. Why invertible domain wall is a duality? Obvious because for us, the domain wall is the morphism. If the domain wall is invertible, it simply means the morphism invertible. Morphism invertible is what? Is the duality? Is automorphism? Yeah. Yeah, because domain wall is the morphism. Yeah. So that's we always do this. So we you can use this method very powerful. You're not only to have a this one's invertible. You can consider the domain wall which is not invertible. You can compute anything you want. It's very powerful. But I think the most powerful one is to compute the sandwich of a gapless domain wall. On the one side, well, I know people, I know currently it's popular that to compute the sandwich when here is gap, here is gapless. Yes, our theory definitely cover that. But not only we cover that, we can also compute here is gapless, here is gapless. Well, you may say, wow, this is the same, right? You do a double folding, you this become a gap that you reduce to that case. But we can also do the following one. We can even make the bulk gapless. We can still compute it, you know? That become a high. So what I'm trying to say is that we have a more complete theory. From the more complete theory, you can do various things if you want. Yeah, become more flexible. Certainly you can play with a SymTFT. You can you can compute. Oh, here's the one comment I want to make is that for condensed matter physics, it's now very natural to consider quantum field theory living on an open disk. But for biology people, they always compute path integral. They want to consider non-trivial domain wall, no, non-trivial space-time manifold. But for us, if you want to only know about the partition function, you don't need to do that because because that's a picture of algebra quantum field theory. All the observable of TDL it's already living on a open disk. And using internal hum, you can recover all the partition function without considering a non-trivial space-time manifold using the internal hum. It's automatic. To recover modular from the category. Which, what do you mean? Modular, you mean ST matrix? But ST matrix is given by the definition of modular the category. Once you have modular the category, ST matrix is already given. Yeah. So yeah. Oh, that's a different. Okay. Yeah. For higher dimension, let me tell you this: the power of this machinery is to forget about estimation. It's provided by a powerful theorem. It provided by a powerful theorem, which was proved first by myself, actually, and the Muger and Kitaev at the same time. I think Kitaev and Muger perhaps proved it at the same time. And on the one side, you want a modular invariant CFT. The condition very complicated a lot. You have to do it very carefully. Okay, most of physics is only check about the so-called modular invariant for partition function. That's not enough. If this one is complete, this is complete modular, including modular invariant, all the higher genus the correlation functions. Okay, so this is more complete. There is a non-trivial mathematical theorem tell you modular invariant CFT is exactly equivalent to Lagrange analogy. Here, you want to define the modular invariance, you definitely have to use the modular data, right? ST matrix, that kind of very complicated. But after you do this, you don't need to. Look, here's all topological, okay? There, you can forget about ST matrix. Here, you can even forget it more. At this level, ST matrix is hidden in somewhere. Yeah. So the power of this is that you don't need to solve ST matrix. You don't need to solve modular invariant. You can get it. And what's the Lagrangian algebra? Lagrangian algebra is one-to-one can be all recovered by internal Hom. You don't need to worry about it. You don't need to worry about estimation. That's the power of it. For higher dimensional case, this is exactly the same. Forget about estimation because higher dimensional estimation is hard to formulate. But our theorem tell you no, you don't need to worry about it. Using the internal Hom is the solution is automatic. Of course, it's hard for you to believe because the foundation of open-closed CFT, mathematicians have been trying for many, many years, work on it very hard to reduce the original formulation of modular invariance or higher genus modular invariance in a precise way. You do reduce it, eventually become Lagrangian algebra. You see the definition of Lagrangian algebra that does not need the SD matrix at all. Only thing you need to do is check the quantum dimension. But you might ask, why? Such a simple condition is just summarize all the modular invariants? Yes, that's just magic. And this one tell you, this formula tell you why it's magic. It's automatic. This formula tell you see on this side there's no ST matrix. It's just everything's topological, right? It's hidden there. I know it's hidden there, but let's forget about it. Okay, you're doing all more geometric thing, and you fuse them, you squeeze them. Okay, dimension reduction, you do that, and this is automatic modular invariant. So for higher dimension, you also do the same game. You don't need to worry about the higher dimensional modular invariance because that become complicated for sure. The genus, so 1 + 1 is already very hard. If you consider higher dimensional modular, it's even harder. But our theory tell you, no, you don't need to do that. This takes many, many years simplification in order to achieve this level of simplification. Yeah, 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 yeah. No, I don't know. We hope that we suspect that there will be something similar, but no mathematical foundation. If you're a mathematician, you'll be more cautious. You can only say we expect something similar happen, but there is no mathematics available. Yeah. It's very difficult if the category have a object go to infinity and there are issues. Even computing the dream field center is not done. So I for many years ago I already urged some people in the in the 中科院 this is a beautiful project. You should start working on it, but nobody work on it. So no mathematician really seriously work on it. I think partially because fusion category is already reached. There are a lot of results you can do for non-fusion continuous symmetry. Although it's important, nobody work on it. I know, I know. But categorical is non-trivial. So I don't know. I hope I have a student to work on it, but I don't have a student. Yeah, yeah, not trivial, invertible. What? When A is gapless, you want to know what is the auto equivalence. Oh, oh, I don't know. We have a complete calculation. If you want to define the notion of automorphism, you have to preserve perhaps everything. So for on the VOA side, you have automorphism, and on the topological skeleton side, you also have a equivalence, I guess. Yeah. Well, I don't know. There is a tautological way to define it. I don't know whether it's a good one or not. You can using the complete mathematical data. We have the complete calculation, right? You just say which one uh, when they're same. Well, the VOA have to be isomorphic, and topological skeleton have to be isomorphic as a integrated fusion category. This is tautological. I don't know whether that's you want or not. Yeah. Can you say it again? What? Yeah. There is a canonical gapless boundary. Yes and no. If you assume every multi-sensor category have a VOA realization, then I will tell you yes, there is a canonical one. You can sort of canonical. Given by this one. Um, so I think what you're asking is this. Um, uh-oh. I think what you're asking is given a pair, multi-sensor category C, right? You ask, uh, are there any gapless boundary can be called canonical? But you know that according to our theory, there are infinite dimension. There are infinite many of them, right? For example, you stack a lower dimension CFT, you always form a boundary. Our theory cover that. But if you want a canonical, you probably have to assume reconstruction theorem. That means there is a VOA V such that mod V is C. But such V is almost never the unique. In general case, not unique. So there's no canonical one. Okay, but up to this subtlety, there is a canonical one. Is given by so the topological skeleton is given by C enriching itself. Okay, and C just mod V. Okay, and in this case, you can call that your canonical. Canonical up to the choice of V. V, there in general more than one V give you the same multi category. Huh? No, it's just assumption. That's assuming this assumption. Okay. If you don't have the assumption, then there's no canonical one. Okay. Right. It's not no. It's not no. This conjecture have been there for many, many years. Uh, in this word, there's only one guy working on it for many, many years called Terry Gunnan from Canada. And last year, a rumor came out from him. He said that there is a hint that this theorem, this conjecture might be wrong. A hint might be wrong. Okay, it's not a proof. Who? Jones. Oh, yeah, because he care about the sub-factor. He really care about the examples. Yeah, yeah, 重构文. Yeah, right, exactly. Well, I want to make a comment. The funny thing is that when we wrote that paper, we wrote a comment. The comment says, according to our theory of a gapless age of topological order, we don't require this theorem to be true. That means for every, for this conjecture to be true, let me write it down. For every modular tensor category C, there is a VOA V such that C is isomorphic to mod V. Okay, this is called a reconstruction conjecture. Okay, we made a comment. Our mathematical theory of gapless age does not require this to be hold. This become a puzzle for me. Why? Because if a physical theorem does not require this conjecture to be true, why it have to be true? So we cast doubt on this conjecture in our paper because our paper simply tell you, our theorem simply tell you, you don't need this to be true. So physics of a mathematical theory of the gapless age does not require this to be true. We're hoping at that point, we're hoping that our theory can give a hint to this conjecture, but it doesn't. It gives a weaker assumption, much weaker than this. So I feel like so at that point I already have a doubt. So that's why I asked Terry Gannon, what's the current status? Because he always believed those. So, but to my surprise, he told me last year that he find a hint of a counterexample. Right now, I don't know. Thank you, thank you. Yeah.